Welcome back to Surviving Networking and IT. My name's Sean, and we're going to go ahead and finish out the series with setting up a Mikrotik Home Lab with GNS3 and VMware. And in this video, we're going to go ahead and go over Spanning Tree Protocol, also known as STP, and why it's still valid today. Let's go ahead and go through why it's important today. Frequently, you'll have an environment, let it be a home environment similar to this, where you have one router and then you have multiple switches. Let's go ahead and get rid of this label over here. And let's say you have one router and a switch for the different rooms. You have one for, say, a living room, one for a bedroom 1, bedroom 2, bedroom 3. And they all daisy chain through. And what will happen is if this switch 1 goes offline, then these other 3 switches will go offline. And what one would think it would be smart to do is have an additional link or redundant link. And you would think, hey, let me just go ahead and connect switch 4 also back to the living room or wherever else I can get this connected back to the router. And in this, you would think this would be fine. However, if you do not have spanning tree enabled, connecting something like this will actually break your network. In 60 seconds or less, it'll break your network. Because what will happen is your network will receive a broadcast from one of these devices. It can be from any PC whatsoever. It'll come into the switch, and a broadcast by definition has to go out and be flooded through all ports. So the switch by design will flood it out through this top port, which will go to the router. Then the router will push it through this, we'll push it through the switch 4, and then come back down to switch 1. Well, the switch, again, once it receives a broadcast, it is, by design, supposed to send that broadcast out to all ports except the source port. So then it sends it back out this port, and then goes back again. And then this is called a loop. It goes back and forth hundreds and thousands of times. And eventually, it'll clog up the network so much that your PCs won't be able to do anything whatsoever. Sometimes they'll even lock up switches. I've seen it reboot routers. It is not a good environment. However, if you have spanning tree available to you and you can turn that on your devices, then this is a valid configuration that will not break your network. Let me go ahead and delete this, and we'll go ahead and talk a little more about spanning tree. So spanning tree essentially takes your redundant links and disconnects one of them somewhere within the network that is least preferred, and allows that to stop the layer 2 loops from happening. Even though you physically haven't unplugged the cables, one of the ports will actually disable itself to automatically protect the network. And it does this with a few different roles and statuses. Let's pull this up with the different statuses. Okay, let's see, it states, okay, roles. So you have roles tying with this. And we have root ports, which are the best port on each switch to get back to the root bridge. If you're not familiar with root bridge terminology, that is basically the most preferred switch in the network. That is where your core of your switching should take place. More on that later. A designated port is a port with a BIS route on to the root bridge on a link that's usually on the opposite side of a root port. And a designated port is all other ports that are put into a blocking state. Usually it's just one port within the network, depending on how many redundant links you have set up. And here's the states for the ports right here. So we have disabled, a port that's shut down; blocking, a port that is blocking traffic; listening, it is not forwarding traffic and is not learning any MAC addresses. Then we have a learning state, which is not forwarding traffic, but it is learning MAC addresses. And then it goes into a forwarding state, which is sending and receiving traffic as usual. Now you're wondering, how do I tell which one of these is going to be my root bridge, my root switch. And essentially, there's an automatic election that happens, but you can influence that election. And the automatic election happens by the root bridge ID, and that's a combination of a setting and a MAC address within each switch that participates in the spanning tree. So let's go ahead and make sure spanning tree is turned on all these devices. I'm going to go ahead and pull up the router. That will be participating in this. Let's see, R1. Yep, let's go ahead and refresh. We're going to connect to R1. And here we're in our bridge. We're going to open bridge 1, verify that STP is enabled. We're going to go ahead and we're actually going to set this to RSTP. And we're going to set the default value of 8,000. Apply. And normally I'd show you the status, but we're going to go ahead and check the other devices first to make sure they're connected and have STP turned on. So let's go ahead and connect to the remote neighbor. Oh, come on. Connect. All right, switch 2, switch 3, switch 4. There we go. 1, 2, 3, 4. Close Winbox down. And we're just going to quickly check the bridge for each one, make sure STP is enabled with the default value. Okay, of 8,000. That's right. Bridge. STP enabled with 8,000. That's perfect. We'll leave the bridge up because we'll come back to it. STP is enabled with 8,000. That's good. STP is enabled at 8,000. Okay, that's great for switch 1. So all 5 of the devices are participating in spanning tree. Let's go ahead and minimize this Winbox right here. So all 5 of these devices are participating in spanning tree. So out of the gate, right now, if we just look at this diagram, we will not be able to determine which one is the root bridge, and that's fine. But if we want to say we want our router 1 to be the preferred bridge, which is the root bridge, we have to set that setting. And we can influence the election. To do so, we go to the bridge, we open this up, and right here we can change the priority. Now the lower priority is more preferred. So the lowest priority typically wins the election with all the devices in STP. So if you have devices that are all set with 8,000 and you set one to 6,000, I'll go ahead and set this to 4,000 again. And then we check the status. We can see that this is now the root bridge, and it actually lists the root bridge ID, which is the combination of the 4,000 that we just set and the MAC address of the bridge. Now, we go ahead and scoot this over, and let's bring up another switch. Let's bring up switch 1. And we'll open up this, we'll look at the status, and we can see that this also recognizes the root bridge as the X4000 and the MAC address of the router right here, of the bridge of the router. Now let's just say we wanted the switch 1 to actually be the root bridge. We can go to the STP setting and set this to a more preferred priority. So we'll just say we'll set this to 3,000. And what we're going to do is we're going to click on status over here just to watch this on the fly. As soon as I click apply, not even a second later, this updates with the appropriate root bridge ID, and it now knows it's not the root bridge. I'll go ahead and put this back. click apply. And about a second later, we see that this is now the root bridge, and it recognizes the bridge ID with that. This is important to know. The more preferred bridge and root bridge always take priority over everything else. Now let's go ahead and look at some other notes on this. So we've talked about roles, we've talked about states, and now let's talk about the process of how STP begins. Bring this over. So it first starts off with electing a root bridge. This happens by the lowest MAC address or the priority most preferred priority. If all priorities are equal, then the election will happen by the MAC address. Whichever has the lowest MAC address will be the root bridge. After that device is set as a root bridge, all switches will then set its port that is closest to the root bridge as its root port. I'll repeat that. The port that is closest to the root bridge will become the root port. So on switch 1, the root port is this one right here. I'm going to go ahead and just get these labeled so we can keep track of it. This is our root bridge. This port is the root port. And let me change all the colors on this. Text edit, color, make this an awesome green. Oh, come on, text edit, green. Okay, apply. There we go. So that's a root port. In this case, this is a root port. In this case, this is a root port. And in this case, this is a root port. So all switches will have one root port. It won't have more than one root port unless you have more than one redundant link and using a more advanced STP called MSTP. But in this case, we're just going to use a root port. So now on the other end of every root port will be a designated port. It's always a designated port, and this means that port is up and receiving traffic in, typically from a root port. On the root bridge, every single port will be considered a designated port, always, unless it's not connected or if it's admin down. Well, let's go ahead and set the designated port. So at the other end of the root port on this link, it'll be a designated port. Same here, and same here. So in this diagram, if we log into each switch, we can verify that this is the case. So we're going to go ahead into the router. We're going to look at the ports, and we see on Ether 2, it's the designated port. That's the role of the designated port. And we can verify it right here by holding your mouse over it. This is on R1, Ether 2. That's the connection right here. And we'll go ahead and rinse and repeat. I'm going to go to ports. We'll expand this over. And now we see Ether 1 is the root port, which is heading to the bridge. And we're going to verify that on switch 2 as well. I'll put this over here, and just so we can have some discussion about this in a second. Go. Oh, come on. There you go. So we have Ether 1, and that's its root port. And if we look down here on Ether 24, that's the port that connects over to switch 2. That's a designated port. That's the opposite side of the root port, which is for Ether 1 on switch 2, if we look at the diagram. So we verified that this is the layout of all the ports, which means data is flowing and completely functional. Well, let's say we want to make this redundant. We want to make this reliable. We want to make sure that if switch 1 or 2 blow up, that switch 3 and 4 still has a connection. So we're going to go ahead and connect Ether 24 to the root bridge. We'll connect it to Ether 3. That's a part of this bridge. And now we have a loop. So this will change things. This will change things a lot. One, we won't change anything on the root bridge because the root bridge always has its ports as designated ports. But this will change how the root ports are for switch 2 and 3, as well as the designated ports. So I'll go ahead and move those over to the side here. And we're going to talk about how this is going to function. So the root port decision is by the lowest cost to get back to the root bridge. And the cost in Mikrotik is determined on a per port basis. We'll pull up switch 2, and it's based on the outgoing port number or outgoing port. So if we're on switch 1 right here, and we're going to go to Ether 1, this has a path cost of 10. And if we look right here, it's verified that to get back to the root, this has a cost of 10. Go ahead and turn this over a little bit so we can make this easier to see. Root path cost. That's fine. So, and by default, Mikrotik uses a path cost of 10 for every type of link it has. Other vendors do it differently, where bigger links are a more preferred cost. So a 10 gig link will have a lesser of a cost than a 1 gig link, and so on and so forth. In Mikrotik, it is not done that way. So every link is a path cost of 10. So we can say, hey, for switch 1, it takes a path cost of 10 to get to the root bridge. Well, for switch 4, it's going to be the same thing. It has a root path cost of 10 to get to the root bridge. But switch 2, let's see how this is going to work. So this has a path cost of either 1020 or 102030. Well, since 20 is less than 30, that's going to prefer that direction over the other way. So we're going to put the root port back over here. And we'll put the designated port back over here. And for the switch 3, it's going to do the same thing. We're a root path cost of either 102030 or root path cost of 1020. It's going to prefer the 20. And then we're going to set a designated port right here. And typically, you would think this is how it's supposed to be. This is how it's working. Unfortunately, no. This is how our minds would like to think and just magically work. However, one of these links has to break, otherwise we're going to have a loop. We have to determine where that's going to be. And right now, you can always determine a root port will never be disabled and blocking. Let's remember this. A root port will never be disabled and blocking. And also with that, the opposite end of a root port will also never be blocking. So this root port will never be blocking, neither will this port. This root port never be blocking, neither will this one. And same thing with over here. And if we duplicate these, I'm going to duplicate both of these real quick. We need to describe the other links. Either this one will never be blocking. And same thing with that one. Hey, we got that one already. Okay, so we only missing one. So this one will never be blocking, that will never be blocking. This one will never be blocking, that will never be blocking. The only way it will be blocking is if 2 designated ports are linked together. So we have to determine which one of these 2 designated ports will actually be blocking. Well, that happens by an election again. Usually it's the lowest bridge ID that it'll be the more preferred. And let's see how it's going to work in this case. So we're at switch 2 and switch 3. So this is switch 2, and I'll pull up switch 3. There we go. I'll increase the text just a little bit so we can actually see it. Go to ports. Okay, well, it is not liking me to do the 50-50 share today on this screen, so let's go ahead and do it manually. There we go. And so we're looking at ports. It'll be port 24, and it's going to be then Ether 1. So Ether 1 is set to designated. Of course, its root port right here is Ether 24 going over to switch 4. But Ether 1 is pointing to switch 2 on Ether 24. And look, this is an alternate port. That's another state that is commonly shown as alternate. That's another form of, it'll be a blocking port. And we see this has a path of 30. Now that's normal. Now if we go ahead and double click on this, we can click on the status. And we see this role is alternate. And it's not learning, it's not forwarding traffic. So this means this port is blocking traffic completely. Now let's look at the bridge IDs and see which one has a more preferred bridge ID. And let's see, this is 0CAB and this is 0CBC. So this port over here on this switch has a lower bridge ID, and that is going to make it a more preferred bridge to use, which makes this the designated port and this one the alternate port. Now, if we wanted to change that around, let's just say we want to make this a more preferred bridge. We just change the bridge ID using the priority. Let's just change this down to 7,000. Click apply, and magically, you'll see on the right-hand side, it changed to an alternate port. Now this port is the blocking port. We go to status. We see it's not learning, it's not forwarding, so it means it's not passing any traffic whatsoever. We'll go ahead and put this back. We'll set this to 8,000. Click apply. And now this port is more preferred. That's a designated port. And this port is now an alternate port and is blocking. Let's go ahead and minus these and take a look. So we can actually see this was actually not designated port. This actually was a blocking port because this MAC address on this switch 3 was a lower MAC address and is more preferred. The great thing about this is that you can break any one of these links and it will magically reconfigure STP to reconverge in a way that devices will still stay online. So let's just say this link right here between switch 2 and 1 broke. I want to click on this. And now, by looking at the process, this is no longer a designated port. This will no longer be a blocking port. This will probably stay a designated port, so the root port will flip over here. And now the root ports will all stay the same right here. So let's go ahead and look at switch 2 again. This is switch 3. Let's look at switch 2. Oh, come on, switch 2. Where'd you go? Let's see, switch 1, 3, 4, 2. Switch 2. Okay. We have switch 2 right here. And Ether 1 is disconnected, so it's going to be disabled, which we expected. And now Ether 24 is back in play, and it's considered the root port. We'll go ahead and minimize this. We'll put the link back. We'll say, hey, Ether 24 is going to connect to Ether 1. This will go back, be a designated port. I'm sorry, the designated port will be right here. The root port will flip back over. And of course, this will become a designated port. And we'll verify that right here on the fly. And look, this is a, sorry, not a designated port, it's the blocking port. And now the other one will be the root port once again. I hope this kind of makes sense and how Mikrotik handles spanning tree. It took me a while to understand it, and I hope this can at least allow you to practice this in your own labs. If you have any questions, reach out to me. I'm always available on the Discord. I try to help out people as much as I can. But in the meantime, thank you for watching and have a good day.